Morning, everyone. I hope you're enjoying the conference so far. Some absolutely fantastic presentations. My name is Jim Gelder. I'm a technical director in engineering geology for McDonald in Cambridge. Between 2016 and 2019, I was the design lead for the Boston Barrier project. That's a £100 million flood defence scheme to protect 14,000 properties from tidal flooding. The nice thing about being the design lead is you have a fantastic team that works underneath you, and that starts with the co-authors for today's paper, Laura Yushang Shu, Mary Schaefer, and Sergio Solera. But really, it'd be remiss of me to miss an opportunity like this to thank the rest of the team. We had a team of over 200 at the peak of the design on temporary works and permanent works design. That's within the joint venture of BAM Nuttall and McDonald as BMM JV, working on the WEM framework for the Environment Agency. I've picked out a few stars. There are about 20 of them. Steve Lauder is the project manager for the JV. Charlie Bell took over from me as design lead, and Adam Robinson and Jim Anderson are the key figures for the Environment Agency as the client. So we're in Boston, Lincolnshire, on the east coast of the UK, on the side of the Wash. And the flood defence comprises a sheet pile river wall on the right bank of the Haven in Boston, a tidal barrier structure, a little bit like a small Thames barrier, and then new quay wall all the way along the port of Boston on the left bank, and then a new set of gates to enhance the flood protection for the Port of Boston. This bit, if you'll have us back next year, is under detailed design and construction at the moment. The rest of it is really well on its way to being built. So I'm going to talk through 7 piling details, A to E. They're on the screen there, but I'll show you which one we're looking at as we go through the talk. Quick word on ground conditions. Ground conditions are actually relatively straightforward in the natural sense. We've got some alluvium over glacial till, and the alluvium is very soft. But significantly in the Port of Boston, the made ground is fraught with risk. Lots of known, but also lots of unknown and unknowable buried obstructions within the port estate. And that was a key feature of the design, as you'll see as we go through the talk. So the first section is section A, and this is by a long way the simplest. It's just cantilever sheet piles, because you've got a very low retaining height to the existing riverbank here. So it starts at the end of the job and comes down the right bank to about here. And they're towed into the glacial till, so they're longer than they need to be for retaining to affect a seepage seal in the flood condition. We start to get really quite complicated really quite quickly though. Section B is upstream of the barrier. One of the key risks we faced on the project was noise. You'll see down in the bottom right corner the barrier cofferdam. There's some big piles in there, CX110 impact hammer required to drive those into the stiff glacial till. The houses are very close, and they were also prone to vibration as well. So rather than an anchored sheet pile wall, we actually constructed a diaphragm, so 2 rows of piles tied together. And this is the line of anchor piles that's coming in with the crane, and then we were able to over here put the noise barrier, use the anchor pile wall as a foundation for the noise barrier. We had no noise related delays, and when you consider that all of this piling is on the critical path to get the barrier in, and the jack up costs £30,000 a day, that was a great achievement for the whole design team. Next section is section C, slightly downstream of the barrier, and we've now got a retained height of 10 meters. And I'm just going to come and show you this in in the model. So section C is at this location. This structure here is called an emergency lay-by facility. It's to allow people in distress to get off the river if the barrier is closed. And the reason I wanted to show you this really was just to sorry, bear with me. Here we go. Yeah, is just to show you that the value of the BIM model. Starting to get a little bit more complicated, and you can hopefully see that we're introducing H piles in between the tie rods, and so the BIM model helping to coordinate that element of the design. Next section is section D, where that theme really takes hold. What we've got here is the twin wall cellular cofferdam that we used as a piling platform to install and construct the barrier. So dark grey piles are permanent piles, light grey piles are temporary piles, and there were some existing seepage piles in there as well that we needed to coordinate around. So really detailed interaction between the temporary works design team doing a very difficult piece of temporary works design and the permanent works design team doing what would be a relatively straightforward design if we didn't have to have all this interaction in 4 dimensions. The sequencing was really key, and the ability to talk around the BIM model on Teams calls and the like, absolutely fundamental to success. Moving on to the left bank and section E, I mentioned the obstructions, buried obstructions, and that's what I'll focus on now with section E1. So section E1 is in this area here, and if I cut that out, there you go, and drag this down, then you'll be able to see what we were up against. There's an existing quay wall here in blue that's anchored to an existing anchor beam with tie rods at an unknown spacing. There was no tie rods on the as-built drawings, and there are bollards with bollard ties onto that anchor beam as well. But you can also see quite clearly the services that we knew about in the model, but also we found lots of unknown and unknowable services and also buried obstructions. So the design was to anchor the wall with 1.4 meter diameter tubular steel piles, 18 mil section, and they were every other pan, so along the front, along the quay wall, and we pre-probed each one of these. We had a sheet pile on a Movax rig that went and proved no buried obstructions at each tubular pile location, and where we did hit obstructions, there was flexibility in the design to move the pile in X and Y a little bit to get around the obstructions. That flexibility absolutely key to managing the risk of buried obstructions and buried utilities on the left bank. The next section, sorry, is section F. We had to build 3 crane pads, and I'll show you section F3 in the model just now. So there's the crane pad for section F3, and what we were able to do here was connect up and use as anchorage the new sheet pile wall anchored to the piles for the crane pad. I'll just highlight one of the anchors there. So you can see that the anchors for the quay wall come off this wailing beam to the first row of piles. but utilize all the piles and the raft in that crane pad to anchor the quay wall, and that saved us having to put in an additional anchorage system. The final section to talk through is section G, and this was the most congested part of all. So as with the others, I'll start here. Section G is in the center of the job, and what I'm going to do is I'm actually just going to rotate around and look at it from the other side, because this is the view that you get from the image that's in the paper. So there's the shed that we were just looking at. So now here's the new quay wall. The old quay wall in this location is anchored to a piled trestle table rather than an anchor beam. There's an existing crane pad on the ground here that is piled, but we couldn't really get as-built records for those piles, but we knew that was also piled. And then we have the new piles going in for our new crane pads either side. So really very really very congested. So the solution was drilled anchors that were designed in the model as much as possible with clash detection in mind, but the contractor obviously had a number of re-drills and had to drill through some buried obstructions as well. But that's how we mitigated the most congested part of the site. The last detail to just talk through is there's a picture of the piling in progress on the left bank. That's taken several weeks ago now, but really advancing well along the left bank. The last thing I wanted to talk about was the control building. So the control building also on the critical path, because we had to get all the M&E in there to commission the barrier. And originally it had to be piled to hold the control building down. We did some nice work in the control building to reduce the loads, and we did a zone load test to prove that we could manage with a raft foundation. That meant that we were able to design out 70 piles, reducing the buried obstruction risk, reducing program risk, health and safety associated with buried obstructions, managing buried obstructions and services in contaminated land, reduce the risk of critical delay, and of course the cost and carbon reduction as well of the piles that we didn't install. So that was another bit of work that we were really pleased about as the design team. So a real rattle through an awful lot of piling work, an awful lot of design. I think the key message that I'd like you to take from this is the value of the BIM model in drawing together the design and construction team and also external stakeholders as well, and the diversity of teams that you can get looking at problems and getting inspiration from unexpected places. We've done some really great work as the JV at Boston that we're all very proud of. So I hope that was enjoyable. Thank you very much, and we'll catch up later for questions if there are any. Thank you.